So thank you very much for coming. So this is a session of JavaScript bindings. So I am Haraken, so from Tokyo. So Tokyo is here. So nice to meet you. So anyway, so in this session, I would like to cover 4 topics in V8 bindings. So code quality and memory, including Oilpan and performance and security. So before starting this session, I would like to say thank you to these people who are contributing a lot to V8 bindings. So in this talk, I would like to cover V8 binding projects that have recently been accomplished by these people. So so the first topic is code quality. So the first effort about code quality is rewriting the ideal compiler in Python. So what is the ideal compiler? So the ideal compiler generates a binding code between V8 and Blink. So as you know, so in the Blink codebase, there are 650 ideal files. And for example, if you give node.idl to the ideal compiler, then ideal parser parses the ideal file. And the parsing tree is passed to the code generator, and the code generator generates node.h and node.cpp, which are binding code between V8 and Blink. And currently, this ideal compiler is written in 8,000 lines of Perl scripts. And as you know, Perl is a messy programming language. So as a result, this ideal compiler is very messy. So we are rewriting this ideal compiler in Python, and we are also using Jinja template engine for code generation. And as a result, it's much more readable and maintainable. And in our experiment, the startup time of Python is slightly faster than the startup time of Perl. So we are expecting slight performance improvement in this ideal new compiler. So I think we can run the new compiler in 2 months or 3 months or so on. The second effort around code quality is cleaning up IDL attributes. So as you know, Blink has a lot of ideal attributes. For example, enable at runtime, constructor, named constructor, reflect, and so on. The problem of these ideal attributes is there are too many ideal attributes. And the too many ideal attributes have embarrassed Blink developers. So we are reducing that number. And actually, since Blink started in April, so we have decreased the number of ideal attributes from 115 to 61. And they are now well documented in the Blink website. And the third effort around code quality is removing custom bindings. So ideally, 100% of the binding code should be auto-generated by the ideal compiler. So however, in reality, the ideal compiler is not mature enough, and thus a lot of binding code are handwritten in custom bindings. The problem of these custom bindings is that they are buggy, so especially for edge cases. So for example, what happens if you pass undefined to DOM methods, or what happens if DOM methods throw exceptions? So these edge cases are very buggy in these custom bindings, so we are killing these custom bindings. So actually, so we have removed more than 1,000 lines of custom bindings since Blink started in April. So however, we still have 11,000 lines of custom bindings, so we should remove more. So so here is a summary about code quality. So we have been improving the ideal compiler, but we need to improve more. And actually, I have seen a lot of Blink developers having trouble in writing binding code. And basically, Blink developers are never interested in writing binding code. So what they are interested in is just implementing new web features. So bindings shouldn't block Blink developers from implementing new web features. So we have to improve the ideal compiler and refactor the binding code more. So volunteers are welcome. So the good news is that there are a lot of low-hanging fruits in this area. So for example, removing custom binding code is not hard. And another good news is that we have active reviewers covering all time zones. So Christoph is working in East US, and Anabas is in West US, and I am in Japan, and Jochen is Germany. So it's perfect. So the second topic is memory. So the first effort around memory is making V8 handles safer. So basically, there are two kinds of V8 handles, handle and persistent. So handle is an on-stack handle that is associated with the handle scope that is allocated on the stack. So handles are automatically deallocated when the current handle scope exists. So on the other hand, persistent is an on-heap handle, and you can create a new persistent on the heap, and persistents are not deallocated until you explicitly call dispose. And the persistents can have weak callbacks. So this is the handle system in V8. And what's the problem? So the problem happens when two persistents point to the same V8 wrapper like this. So imagine that a weak callback of persistent 1 is triggered, and the weak callback calls dispose. Then the V8 wrapper is gone. So as a result, the persistent 2 becomes a dangling pointer and will cause a use after free in the near future. So this is the problem. So actually, there are two solutions for this problem. So the first solution is to introduce reference counting to persistent handles. So however, we didn't take that approach because of the overhead of reference counting. So alternatively, we adopted a solution that disallows copy constructors of persistents. So needless to say, by disallowing copy constructors of persistents, we can make sure that it becomes impossible to have a V8 wrapper that is pointed by two different persistents. And actually, we have removed all persistent copying from the Blink codebase and deprecated all fragile V8 APIs that can cause this problem. And the second effort around memory is removing script values. So what is a script value? So script value is a class to hold a V8 wrapper in DOM objects like this. So internally, script value is realized by holding a persistent to the V8 wrapper. So as you can see, script value is convenient because DOM objects can keep arbitrary JavaScript object from web core. However, it's very dangerous. So specifically, there are two problems. The first problem is it can produce reference cycles. So for example, a DOM object can hold a script value to an arbitrary V8 object. And assume that there is a node and its wrapper. So the node wrapper is keeping a reference pointer to the corresponding node object. And also assume that this node object has a reference pointer to the DOM object. And there is a reachability in the JavaScript side from the V8 object to the wrapper of the node object. So in this case, there is a circular reference. This is a problem. And the second problem is script value can leak V8 wrappers between isolated words. So isolated word is a concept that corresponds to a content script in Chrome extensions. So the contract of a content script is that so two content scripts must be isolated in terms of JavaScript objects. So to guarantee the contract, so we are creating separate V8 wrappers for each isolated word. So specifically, for one DOM object, we are creating separate V8 wrappers for each main word and isolated word. So by doing this, we can guarantee that two content scripts must be isolated in terms of JavaScript objects. So what's the problem around the script value? So the problem is that script value breaks this contract. So for example, look at this code. So basically, so isolated word is a concept that is managed in the binding layer. So Blink does not know information about from which word the script value is created. So consequently, Blink is very happy to return the script value to an isolated word that is different from the isolated word from which this script value is created. So in other words, script value leaks between isolated words. So this is the second problem. So in summary, script value is convenient but dangerous. So we are removing script values one by one, but this requires a substantial amount of whiteboard work. So we are doing somehow. Okay, So the third effort about memory is Oilpan. So Oilpan is a project that aims to replace reference counting in Blink with a general garbage collection. So in short, Oilpan is a garbage collection for Blink. So what's the goal of this Oilpan? So we have a couple of goals. So the first goal is simpler programming model in Blink. So in Oilpan, you no longer need to worry about reference cycles because garbage collection can take care of everything. So this means that you no longer need row pointers and worry about their lifetime. So for example, in the current Blink codebase, there are a lot of back pointers, so like this. So for example, class A holds a reference pointer to B, and class B wants to hold a reference pointer to A. However, we cannot use reference pointer because it creates a reference cycle. So we are using a row pointer to A and carefully clear out this row pointer when B dies. So this is very error prone, and actually this has caused a lot of use after free bugs in Blink. However, in Oilpan, Oilpan will solve this problem. And the second goal is better security. So as I mentioned now, reference cycles don't have to be broken by holding row pointers, which you can easily forget to clear out. So in Oilpan, there is no use after free in principle. Yes, and the third goal is DOM becomes traceable. So with Oilpan, we can completely understand reachability of all objects in JavaScript and DOM. So this means that we can create an excellent developer tool to diagnose memory leaks. And in long term, DOM snapshotting will also become possible. And the fourth goal is better ZC integration between V8 and Blink. So currently, V8 has garbage collection, and Blink has reference counting. And these two memory management systems are connected by the binding layer using super hacks. And less than 5 people in the world are understanding this hack. This is the problem. So however, Oilpan will make this world more beautiful. So after Oilpan, V8 has a garbage collection, and Blink has a garbage collection. And they are connected by cool integration. So this is cool. So the current status of Oilpan is we are developing in a public experimental branch. And we have moved some DOM objects in modules, so web audio, IndexedDB, and game API, and so on, and the CSS hierarchy and the node hierarchy to Oilpan's heap. And we are starting performance work to make the regression down to 0. So we are still experimenting. So we are planning to upstream Oilpan once performance and programmability problems are resolved. So in summary, so in short term, we are killing use after freeze and reference cycles so by making V8 handles safer and removing script values and so on. And in long term, Oilpan will solve a ton of memory problems we currently have. Okay, so the next topic is performance. So this is a Dromio result in Windows between Firefox 22 and Chrome 30. So as you can see, Chrome is 20% slower than Firefox. So this is a problem. So in Windows, Chrome is 20% slower than Firefox, although in Linux, Chrome is 10% faster than Firefox. So I agree that Dromio is just a micro benchmark. However, I think this is a problem. So we should make it faster. So here is one frequently asked question. So is Dromio a good benchmark? So this is a good question. So I agree that Dromio is just a micro benchmark. So however, it's true that Dromio is testing very common code paths in web applications. So in my honest opinion, so I think it's worth watching Dromio performance. So in other words, we shouldn't regress Dromio or lose in Dromio. So however, when doing some optimization work, it is important to profile real-world web applications, not Dromio. So this is my opinion about Dromio. So with these motivations, so I think it's still important to make Dromio faster, but we are recently moving our focus from micro benchmarks to real-world web applications. So for example, so we are implementing a sampling profiler in Chrome tracing. So this sampling profiler can visualize what percentages of the main thread executions are charged on what performance factors. So for example, this profiler can visualize what percentages of the main thread executions are contributed to layout, style calculation, major garbage collection, DOM attribute getters, and so on in real-time manner. So actually, I wanted to run this profiler by today, but I couldn't for some reason, so I will run it in a very near future. And another topic about performance is build performance. So the motivation is that the idle compiler is slow. So specifically, if you touch any IDL file, all 650 IDL files are reviewed. So this implies that all dependent header files and CPP files are also reviewed, and this becomes a serious problem in Mac, Windows, Android builds where the build speed is very slow. So we already have an optimization plan which guarantees that only necessary IDL files are reviewed. So we are planning to make this optimization in the near future. So in summary, so we are moving our focus from micro benchmarks to real-world web applications. However, it's still problematic that Dromio is slower in Blink than Firefox. So let's make it faster. And one good news is that no one complains about optimization work. So when you are implementing new APIs or adding new features, someone will definitely complain about your work. So however, in the case of optimization, no one will complain as long as you are making something important faster. So volunteers are very welcome. Okay, so the final topic is security. So regarding security, we are improving binding integrity. So the motivation is that the binding layer is the best target for security exploits. So why? So this is because type information is lost when converting DOM wrappers and DOM objects and V8 wrappers. So specifically, so we are doing static cast and reinterpret cast when converting DOM objects with wrappers. So type information is lost here. So this is a place as a target for the security exploits. So we are adding security checks to prevent the security exploits that abuse types and use after freeze. So what we are doing is, in a nutshell, so whenever Blink returns V8 wrappers to V8, we check that the wrappers have correct types. So specifically, what we are doing is, when we create a DOM object, we store the object type into the DOM object. And when we wrap the DOM object to a V8 wrapper, we check that the stored type is still correct. And then store the C++ pointer of the DOM object into that wrapper. So by doing this, when we return the wrapper to V8, we can check that the C++ pointer stored in the wrapper is identical to the C++ pointer of the DOM object. So in summary, it's complicated. So, but anyway, so the point is that the security checks guarantee that DOM objects are always wrapped to V8 wrappers of correct types.
Are we doing that in release builds? Or just
Yes, we are doing it release builds.
Maybe that's 20% compared to Firefox.
So actually, so we don't run security checks for performance sensitive places, so that isn't the reason. Yeah. So it's problematic that we cannot add these security checks for performance sensitive places that are used in Dromio. So yeah, it's problematic. Okay, so thank you for listening. So in this talk, I covered code quality, memory, performance, security in this alphabetical order, CMPS. Okay, so with bindings, welcome contributors and active reviewers are waiting for your patches. So welcome. Yes, so any questions and discussions? Yeah.
This was a great talk. Some colleagues have reported that the same WebGL application on a web page is slower than, say, a native Android app.
Hmm?
Unfortunately, something about how V8 does data calls. There's a lot of work that's done to bindings there. How can we expose performance issues here and really drive performance optimization to the V8 call out layer and the binding layer?
So the question is that in WebGL applications, the binding overhead is very large. So how can we solve that problem?
Yeah, I mean, how can we really create effective benchmarks that track this?
So the benchmarks about that measures the pure overhead to call the binding layer.
Kind of, yeah. How would you do that?
Yeah, so one benchmarks that is mostly affected by the pure overhead of calling back the binding layer is in Dromio. So for example, node.firstChild is doing nothing in the Blink side. So it represents the pure overhead of the binding layer. So I agree with you. So the problem, one of the problem of the binding performance is the overhead for V8 callbacks to the binding layer. So actually, this overhead is 3 times larger in V8 than in JavaScript core. So I know this is a known issue. So, so how can we solve it? So the answer is that there is a benchmark to measure it, and the overhead in V8 is large. So the problem is that we have to make it faster. Yeah. Yes.
I mean, one possibility is if we know something about the WebGL callbacks, maybe we could know that we're never going to allocate an object or something like that, and maybe do something more efficient.
Yeah, and another reason for slowness is that all the APIs have to be very generic. They have to do type checking to make sure that you're passing the right type. And since all this happens inside Blink, the JIT cannot optimize away that. So Firefox have been talking about giving the binding feedback about type control and stuff like that, and possibly to do something similar. Because V8 knows that it has a number, for example, or double, and so our binding does not have that.
Yes, and in case of array buffers, so array buffers is going to be moved from Blink to V8 so that we can apply JITting for access to the array buffers.
And that's going to be a tremendous speed up.
Yes, and actually we want to do the same thing for normal HTML objects, so JITting access to HTML objects. However, the challenging part is that there are a lot of types in Blink, so implementing a dynamic type inference for a lot of types is not efficient. So this is a showstopper to implementing JITting for a lot of HTML objects in Blink.
But maybe the WebGL object is easier in that way.
Yes, 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 yes.
The issue is that you're creating a benchmark to this overhead from WebGL because they have to have two things. The web browser with a whole massive software stack and then some native application. It's very hard to compare those two. If you make some new micro benchmark that compares performance in, Blink or some Blink-based browser versus say another browser that's not Blink-based and goes faster than the other browser, that's sufficient benchmark to continue to expose the performance issue. Browser versus browser as opposed to browser versus native application.
Yeah, another approach you could try is you could have a flag that's stubbed out, put in a stub implementation of WebGL, and just like return texture numbers and ignore everything else. And then you can see like what percent was coming from the binding layer, and like sort of break it down by layer and see where the time is running. And successively mock out less and less.
It's tough because the application developers are actually trying to measure how many graphics objects they should run. So it's kind of easy to just exercise the graphics processor capabilities. I think it's actually challenging to make a side-by-side benchmark, web versus native. Because obviously, if you had that, the native app would be just speed-of-light comparison. And you just optimize the entire web stack rather than spend something like that.
So a suggestion I have, there's something with 2D Canvas, something we can do is if you apply a transform that makes your draw out of bounds, it'll trigger an early exit, and then you're measuring almost only the bindings runtime. And you can compare that to the native early exit directly in if you want to build that deep into the whole style.
Okay, so
I don't know if you
question.
can do something equivalent in WebGL.
Okay.
Yeah, I have a couple of questions and a comment. Recently, on a test I was submitting, I found I had to create a custom binding because I had a case where create the ref function. I had to query a state on the space type. You mentioned that you should be able to remove them, but I didn't find any way to not be able to implement a custom binding for that. Kind of misheard you skip value because the union types are not supported in our IDL.
Yeah, we recently supported union type.
Oh, yeah, that recently. Okay, very good. So maybe that'll fix that.
So the core problem is that the ideal compiler is not mature enough. So we have to improve that ideal compiler so that it can auto-generate as much as binding code as much as possible.
And then the final comment is that you describe a very clean approach here, but I've never seen an oil pan that was clean.
Yes. Oilpan is very clean. Yes, beautiful. So any other questions? Yes.
Yeah, you mentioned DOM snapshotting briefly. I was just wondering what would the application of that be?
Sorry, DOM snapshotting.
DOM snapshotting, yeah. What can you use it for?
So DOM snapshotting for what?
What can you use it for? What would it allow?
So the use cases of DOM snapshotting. So, for example, so by snapshotting DOM, so we can store and restore web pages immediately, for example. So, yeah, however, actually, DOM snapshotting is very challenging, so it's a very long-term thing.
Yeah, is it potentially useful for running layout in parallel with script, given like if you want to do a snapshot?
Yeah, in principle, we can use it for that purpose.
With ASM.js, is there hope for reducing the bindings over there? So, any comments on that, or
So,
is there work that's already being done, or?
So I'm not familiar with ASM.js, but Eric, do you know?
Yeah, I don't see how those two things are related. ASM.js is ahead of time compilation.
But if could we factor out the type checking that happens in
So that's a good point. You can probably feed the type info back. That's the same thing with legit. If you know the type of your value, then we should be able to skip some tests.
So any other questions? So partially, yes. Okay, I got it. So your question is that script value, will script value be still needed in the Oilpan world? Okay, so sorry for partially yes. So, so regarding circular references, Oilpan will serve all reference cycles. So we don't at all need to worry about circular references. However, so the problem we need to still address is that script values between isolated words. So Oilpan does not care, does not take care of anything about isolated words. So this should be still addressed in the Oilpan world. So regarding the circular references and memory leak caused by that problem, so Oilpan will solve it. Yes. Yes, so I think you don't need to worry about circular references any longer. So however, so you have to still care about isolated words. So for example, you cannot return the script promise to an isolated word that is different from the isolated word from which the script promise is created. So you have to still care about it. However, you no longer need to care about circular references and memory leaks caused by circular references.
So what do you return to the other isolated world?
So if there is no script promise created from that isolated words, it would make sense to return null or something like that. So, okay, so the last question? Okay, so the final one.
So I really liked your opinion of the Vimeo benchmark, and I'm wondering what your opinion is about some other benchmarks. So Chromium has a DOM perf benchmark. Is that better? And I'm also wondering, Arniwa recently introduced this new DOM benchmark in WebKit. Does that approach seem fruitful or interesting to you, or do you have any opinions there?
So in my opinion, so DOM-perf will be still variable because we have actually caught a couple of performance bugs using DOM-perf. So I think my opinion is that it will be variable to have a lot of benchmarks, micro benchmarks. However, we should focus on real-world web applications when doing some optimization work. So micro benchmarks will be variable for not regressing performance and not losing from other browsers.
Makes sense.
So okay, so I would like to wrap up this session. So thank you very much.